here. So I need everybody to go to page 445. Lesson 7.6, the last lesson of this entire unit. So what we're going to be looking at today, there's quite a few goals and there's a lot of vocab too. So there's another reason why we're taking 2 days on this. There's a lot to learn in this unit or this section. So we're going to apply properties of trapezoids to solve real-world and mathematical problems. We'll then apply properties of trapezoids and use coordinate geometry. So we can't really do geometry without talking about coordinates. To figure out lengths and endpoints of mid-segments, all that good stuff. We will also apply the properties of kites to solve real-world and mathematical problems. And if you take a look at the vocab list, there's a lot. Trapezoid, base of a trapezoid, legs of a trapezoid. Sorry, bases of a trapezoid. Legs of a trapezoid, base angle of a trapezoid, isosceles trapezoid, mid-segment of a trapezoid, kite. So you can see most of our notes are going to be centered around trapezoids because like almost all of the definitions have to do with trapezoids. And then, so quick recap. A trapezoid is a quadrilateral with exactly one pair of parallel sides. The parallel sides are called the bases. So here's our diagram. The ones that are parallel are the bases. We've got base 1 and base 2. It does not matter which one is base 1 or base 2. They are the bases. The other two sides are called the legs. So the sides that are not parallel are called the legs. A base angle is an angle formed by a base and one of the legs in a trapezoid, which basically means that all of them are base angles, right? Because if a base angle is an angle formed by a base and a leg, is there an angle in here that isn't formed by a base and a leg? I don't think so. I think they're all base angles. Anyway, in a trapezoid, so in this particular trapezoid, angle A and angle B are one pair of base angles. And this is where base angles actually make a little more sense because you have to use them in pairs as opposed to individually, because individually they're all base angles. However, A and B are one pair of base angles. C and D are another pair. If the legs of a trapezoid are congruent, then it's an isosceles trapezoid. That's a different idea altogether. So one of the things we're going to learn about has to do with the base angles. We're going to learn about some specific things related to isosceles trapezoids. It's the same idea as an isosceles triangle, where, you know, the legs of an isosceles triangle are the same. So in an isosceles trapezoid, the legs are the same. They're congruent. So let's take a look here. So if a trapezoid is isosceles, then each pair of base angles is congruent. So as long as the legs are congruent, that makes it an isosceles trapezoid, which means that the pairs of base angles, GH, would be congruent to each other. FJ would also be congruent to each other if it's isosceles. If a trapezoid has one pair of congruent base angles, this is 445. If a trapezoid has one pair of congruent base angles, that means it's isosceles. So if you have one pair of base angles that are congruent, one pair of angles in between, on one of the parallel lines in between the two legs, if one of those pairs is congruent, that means the whole thing is isosceles for that trapezoid. And then one more theorem here about some trapezoids is that if a trapezoid is isosceles, a trapezoid is isosceles if and only if the diagonals are congruent. So this is another reason why when we were talking about rectangles and the diagonals of a rectangle being congruent, diagonals being congruent is not enough to say that you have a rectangle because it might also be a trapezoid. So that's why when we're talking about rectangles, that you had to know it was a parallelogram first and then say that the diagonals are congruent to get a rectangle. Because if you don't know it's a parallelogram, if it's just a quadrilateral that has congruent diagonals, it might be a trapezoid, specifically isosceles. So if you have an isosceles trapezoid, the diagonals are congruent. If you have a trapezoid with congruent diagonals, that means it's an isosceles trapezoid. All right. So go and close up the Chromebooks if they're still open. Close them up. Close them up. We're going to start writing some stuff down. All right. Here we go. Red, close it up. Red, close it up. All right, time to do some math here with a really crazy looking guitar. All right, so the body of the guitar shown is a trapezoidal prism. Basically, that just means it's a trapezoid, but it's a three-dimensional trapezoid. We're just looking at the front of it. The front face of the guitar is an isosceles trapezoid, means that the legs are the same. Let's see, the length of AB is 3x minus 2. The length of CD is 3x plus 9. The length of AD is 4x plus 5. And the length of BC is 5x minus 6. Prove that x is equal to 11. So, before we even get started here, which two sides would be parallel on this trapezoid? What are the parallel sides on this one? Wait, which ones are parallel? Yeah. Yeah, AB and DC would be parallel, which means that if we're talking about congruent, that means that AD would be congruent to BC. So if you're trying to solve for x here, the only things that you need to set equal to each other are the expressions with AD and with BC. You do not need the expressions for DC and with AB. Those will not help solving for x. And we have ourselves an algebra proof right here that we're going to be filling out. And so the fact that it's an isosceles trapezoid is given. And then AD being congruent to BC. Take a look at all the reasons off to the side here. These are kind of nice because you always get to choose. We can cross off given. What would be the reasoning for number 2, though? AD being congruent to BC. How do we know that because we have an isosceles trapezoid, that 2 of the sides are the same? Look at the list on over to the left. What thing from the list can we use to say that those lengths are equal or congruent? You guys, put your phones down. Put your phones down. Put the phones away. Emmy. Emmy. All right. So we know it's an isosceles trapezoid. That's given. From the left here, why are we allowed to say that AD and BC are the same? Look over on the left. What over here could we use to say that the legs are congruent? It is a definition, but the definition of a congruent goes from congruent to equals or equals to congruent. What's it a definition of? What shape do we have? It's a definition of an isosceles triangle or trapezoid. Not a triangle, it's a trapezoid. Definition of isosceles trapezoid says that it's a trapezoid with a pair of congruent legs. So that's the definition of isosceles trapezoid that allows us to make that statement. So def of isosceles trapezoid. All right. Then anytime we go from congruent to equals or equals to congruent, what are we using? That would be the definition of congruent segments specifically. So definition of congruent or definition of congruent segments. So definition of congruent. All right. And then how do we know to write this equation? What are we doing to get from AD to 4x plus 5 and from BC to 5x minus 6? Alex? Yeah, substitution. Because it tells us up top in the problem that AD equals 4x plus 5 and that BC equals 5x minus 6. So we're just swapping those out. This is a substitution step. Sub. All right, and then let's see. How did we get from step 4 to step 5? Which one? Close. I don't see that we added anything to both sides, but I do see that we subtraction. Yeah, so it's the subtraction property of equality because I'll just go ahead and write it here. 4x was subtracted from both sides. Minus 4x, minus 4x. 5x minus 4x is x. So that would be the subtraction property of equality. Then what? Then it's the addition property of equality. Yeah, because we have to add 6 to both sides. Plus 6 plus 6. 5 plus 6 is 11. 6 is canceled there. That is the addition property of equality. All right. There's only 2 things left in terms of options. And we're flipping the entire equation around to write x equals 11 because it said to prove that x equals 11, not 11 equals x. What does it allow? That allows us to flip around an entire equation. Yeah, that's the symmetric property. So S, Y, M, M. Also, there are no angles at all in this problem. So definition of congruent angles doesn't really make sense at any point in this problem because there's no angles that we're talking about. All right. So that's how you can solve it using an algebra proof. Again, you won't be expected to do that. But if you needed to, you could. So let's talk about some angles. So find the measure of angle A if the measure of angle C is 72 degrees. So here's A right up here. Here's C right down here. Find the measure of angle A if C is 72 degrees. So the reasoning here says because ABCD is an isosceles trapezoid, C and D are congruent base angles, which means that the measure of angle C is equal to the measure of angle D, which equals how many degrees? If C and D are congruent, how many degrees is angle D? (72). Good. So isosceles trapezoid means that base angles that are on the same parallel line are congruent to each other. So C and D, we go back to the diagram, C right here is congruent to D right there, which also means that angle A is congruent to angle B. We're going to use that as well. So let's hop on down and see what else we got. Because the trapezoid, because ABCD is a trapezoid, that means that the length of AB, segment AB, is parallel to segment CD, which means that the measure of angle A plus the measure of angle something else equals 180. Look at the diagram here. What would add with angle A to equal 180 degrees? This has to do with parallel lines and transversals from a while ago. So if these 2 lines are parallel, you got parallel here, those 2 are parallel. We got a transversal here. That would make A and D same side interior angles in between a set of parallel lines. So the measure of angle A adds with what angle to equal 180? D. Yeah. A and D are same side interior angles. Same side interior angles are supplementary, which means they add up to equal 180 degrees. Now, angle D was how many degrees? 72. So measure of angle A plus 72 equals 180. So 180 minus 72 is going to be the measure of angle A. How many degrees is A? What's 180 minus 72? 108. So A is 108 degrees. Question for you. How many degrees are inside of a trapezoid? Total? 360. Yeah, it's a quadrilateral. Quadrilaterals always have angles that add up to 360. All right, part C. Find the perimeter for the front face of the guitar. we should just be adding all four sides together. AB plus BC plus CD plus AD. We know that X is equal to what? We solved for it in that little proof. What was X equal to? What was it? X equals what? From 11. Yeah, okay. And then we'll go ahead and let's combine like terms first though. So 3 plus 5 is 8. 8 plus 3 is 11. 11 plus 4 is what? So add up all the X terms together. What do you get? 3 plus 5 plus 3 plus 4. 15x. All right, so 15x. -2 minus 6 is -8. -8 plus 9 is what? 1, and 1 plus 5 is 6. So 15x plus 6. Substitute in the value of x, which is 11. So what's the perimeter? $171. Good. 11 times 15 is 165. 165 plus 6 is 171. Centimeters. Cool. So we just did 3 different things with this one problem. We solved for x, we figured out some angle measurements, we figured out the perimeter of the guitar as well. Let's do some isosceles trapezoid coordinate geometry, and then maybe we'll have to be done after this one, because this one might take a few minutes. So quadrilateral QRST has vertices at -8, 4. I'm going to use a pencil for this one. -8, 4 at Q. So that's going to be here. So there's Q. R is at 0, 8. So that's up here. S is over at 6, 8. So that's going to be here. And then T is down at -6, -10. So that's all the way right there. Oh, sorry. Q is at -8, -4, not -4. I'm using a pencil. Of course, that pencil doesn't have an eraser. That is -8, 4, which it is not. -8, -4, which will be here. Did I mess up anything else? Let's see. 0, 8. No, that looks okay. All right. Determine whether it's isosceles or not. All right. So it tells us, first of all, it tells us we have a trapezoid. And we're trying to figure out if this is isosceles. That's the whole idea on this one. If it's a trapezoid, that means we have a pair of parallel sides no matter what. So if Q is here, so there's Q. Nope, that's R. Q's down here at -8, -4. There's R. S is up here. T is down here. Okay, QRST. There it is. So QR is parallel to TS. That has to be true because it tells us it's a trapezoid. So one pair of sides is parallel, and the ones that are parallel are the ones that look parallel. So QR is parallel to TS. We're going to graph it. Then we're going to compare the slopes of the opposite sides. Now, that's not entirely necessary here. It shows you the work just so you can verify which ones are actually parallel. But again, not super necessary here. It's going to be pretty obvious if it tells you you have a trapezoid, which pair of sides is parallel and which ones are not. So that's a little bit of overkill, in my opinion, to figure out the slopes of some other stuff. So I would say skip down to step 3. I mean, the math is done for us, so we can go to step 3 either way. But if this is going to be isosceles, that means that the non-parallel sides have to be the same length, right? So RS would have to be the same length as QT. In order to find distance between 2 points on a graph, we have to use the distance formula. Now, we only have to use the distance formula for QT, though. Why do we not have to use the distance formula for RS? Yeah, you can just count. So what is the distance between R and S? Yeah. because they're going by twos. So 2, 4, 6. 3 spots on the graph, distance of 6 because they're going by twos. So we need to find the distance of QT, which they've got the math out here for us. It ends up equaling the square root of 40. RS is the square root of 36, which is 6 because we can count. But the square root of 40 is not the same as the square root of 36. So that means that 6 is not equal to that, which means it is not an isosceles trapezoid. It's still a trapezoid. It's just not isosceles. So you could use the distance formula. Well, actually, if you're going to find out if something is isosceles in terms of trapezoids, you kind of have to use the distance formula, but you only have to use it for the non-parallel sides. You don't have to do it for all 4. So that was actually pretty quick. And it's actually probably a good thing to use that formula here because it kind of looks like maybe it's isosceles. RS and QT do look very similar in length. And they are similar in length. They're just not exactly the same. And we're able to prove that using the distance formula down below. The square root of 40 is a little bit more than 6. Square root of 36 is 6. All right, mid segments. Let's go back to the warm-up here. We actually have more time. That took a lot less time than I thought. So the mid segments are the segments that connect the midpoints of the legs. And something that we did not mention is the next theorem. So the mid segment of a trapezoid is the segment that connects the midpoints of the legs of a trapezoid. We saw that in the warm-up. What we didn't see in the warm-up, and it's something that maybe some of you noticed, but we didn't actually say it, is the mid segment is parallel to both bases. So if you end up drawing a mid segment, if you connect the midpoints of the legs, that segment is parallel to both bases. So like here, if we were to get to the midpoint of RS and the midpoint of QT, and then just draw a segment that connects those, that segment would be parallel to QR and to TS. So let's take a look. Oh, and it's also equal to, oh, sorry, the other part of it, the part that we did see in the warm-up, it is equal to half the sum of the lengths of the bases. So if you add the lengths of the bases together and divide by 2, that equals the length of the mid-segment. So here we go. Example 3. This will probably be the easiest one that we've done today. You ready? So in the figure, UR is the mid-segment of trapezoid PQST. And we know it's the mid-segment because we have congruent markings here and here, which means that U is the midpoint of PT. We have congruent markings here and here, which means that R is the midpoint of QS. One of the bases is 11, the other one is 18. If you add those numbers together and divide by 2, that gives you the length of UR because it's equal to half the sum of the bases. So that would be 11 plus 18. What's 11 plus 18? 29. What's half of 29? 14 and a half. There you go. 14.5. So if you know the length of both bases, just add them together, divide by 2. That's the length of the mid segment. Now, something else you can do is if you know, let's say, for example, you know the length of the mid segment and you know the length of one of the bases, you can figure out the length of the other base. This one takes a little bit of geometry. This one takes a little bit of algebra to solve. So let's take a look here. Find the missing value. So Rn is the mid segment and it has a length of 24. QP is a base, it has a length of 16.7. We want to find the length of LM, which is the other base, and we're calling that X. What's the value of X? So you can use the trapezoid mid-segment theorem. So the mid-segment Rn is equal to half of the sum of the two bases, LM plus QP. So what's the length of Rn? Rn equals what? How long is Rn? 24. All right. Do we know how long LM is? No. So that's X. Do we know how long QP is? What is it? 16.7. Okay. Now, in order to get rid of the 1/2, instead of using the distributive property and distributing 1/2 to the x and 1/2 to the 16.7, if you just multiply each side by 2, that'll get rid of the 1/2 here, and it will end up equaling what on the left? If you multiply both sides by 2, so times 2 here and times 2 over there, 1s and 2s. 1/2 and 2 cancel out on the right. What's 2 times 24? 48. So that means that the sum of the two bases equals 48 because half the sum is 24, which is the midsegment. So if we subtract 16.7 from 48, that'll give us what's left over, which is the length of LM, which is what? 31.3. So LM equals 31.3. So a little bit of algebra, not much, just a little. All right, we're going to do one more. We will finish trapezoids today. Nice. And then we'll talk about kites tomorrow, and that will be it for this entire unit. So last problem here, mid-segments and coordinate geometry. So it says to find the endpoints of the mid-segment. So first of all, we need to know which two sides are parallel and which ones are not. Which ones are parallel here? What two sides are parallel in this trapezoid? AD and BC are parallel. Good. So the mid-segment connects the two sides that are not parallel. So we need the midpoint between A and B, which will be easy because we can count. And we also need the midpoint between D and C, which will not be as easy, but it's not going to be challenging. You're good. You're good. We'll find the midpoint of D and C, which is not going to be as challenging as using the distance formula because the midpoint formula is a little bit easier to use. So the midpoint of AB, it's actually using the midpoint formula, which is fine. We can. All you have to do is add the x values together and divide by 2. So 0 plus 18 is 18. 18 divided by 2 is 9. That's where the 9 comes from. And then add the y values together and divide by 2 as well. And that will give you the coordinates of the midpoint. So a plus 8 is 16. 16 divided by 2 is what? 8. So the midpoint of AB is at 9, 8. So if we go over 9, which is halfway in between 8 and 10 here, because these are going by 2, and up to 8, that'll put us right there. So that is the midpoint of AB. The midpoint of DC. Add the x values together. We got 1 and 20, which is 21. What's half of 21? 10.5, 10.5. And then if you add the y values together, 4 plus 0 is 4. 4 divided by 2 is 2. So we get 10.5, 2. 10.5 is going to be a little bit harder to figure out on this one because we're going by 2s on the x-axis. So going over 10.5 is like a quarter of the way past 10. But as long as you go up to 2, exactly where it's 2, that's what we're looking for right there. So that's the midpoint between C and D. And I'm just going to get my ID card out again and link those up. Now, it didn't actually tell us to draw the mid-segment, but it just wanted the coordinates of the midpoints, coordinates of the mid-segment. But if we draw it, that would end up providing us a third segment here that is parallel to the original bases. So that's where we'll leave it today. If you need more time to work on lesson 7.5, that's fine. And we'll finish up these notes tomorrow with